Okay, hi everyone. I'm going to start with a question. Who here thinks that they use maps or some kind of geographical data weekly or even daily? Okay, good. I'm going to say that probably all of you do that. It could be the GPS system in your car. Maybe you're checking Google Maps to see where a restaurant or a cafe is. Maybe you're checking the quickest route to a friend's house, checking when the bus or the train is leaving. Maybe you ordered food with the Foodora app or checked if there are any city bikes available close to you. All of these services require really good and accurate geographical data and maps. And we have that in Norway. And I think we kind of take it as a given that we have really good geographical data. But what about the rest of the world? Do you think that it's like this everywhere? Sadly, there are still parts of the world where there aren't any maps at all. There's no information about where there are buildings or roads or land cover or water, nothing. And I'm now going to show you a video that illustrates how this can be a really big problem and shows you the importance of being able to map these areas.
Nilikuja hapa maana nilikimbia ukeketaji. Baba alikuwa ananilazimisha kukeketwa. Ananiambia kwamba nisiende shuleni ili nikae tayari ikifika nikeketwe nimpatie ng'ombe yeni maskini.
During the season of cutting, girls are now, for those who have educated, they are running. They're escaping FGM and they run to be protected to the safe house here. We can't work direct and get there to the village and save them because we don't know which road is short, which road can we use even to go to reach those villages. So mapping villages is helping us to identify some of the villages which have girls who are at risk.
So one girl who just walked inside the house at around Nyamoko village, and she was to be cut on that particular day during night. Nobody knows where the girl stayed, but because we knew it's in Nyamoko, we used our map to go to Nyamoko. We succeeded to go up to the house and rescued the girl.
The work you just heard about is from an organization called Crowd2Map Tanzania. And as you saw, they are working on mapping the rural parts of Tanzania in order to lower the amount of girls that undergo FGM. And in the middle of March, I was at a conference in London, and I was talking about a machine learning project where we are trying to automatically detect buildings in aerial images. And after my talk, this woman came up to me called Janet Chapman, who's working for the Crowd2Map project. And she asked me, is it possible to use this technology to map the rural parts of Tanzania? And would you and Norkart, my company, help us in that process? And since then, we've been trying to figure out how to best help them map the rural parts of Tanzania. But before I go into the details on the project, I should introduce myself. So my name is Mathilde, and I'm a software developer working for the company called Norkart. And I'm guessing Norkart isn't that familiar to you guys. We are a software company working with geospatial data. And we're one of the leading providers of both GIS data, or geographical data, and software in Norway. I think we're delivering apps and APIs to 90% of all the municipalities, as well as insurance companies, engineers, architects, and so on. So we do all sorts of software with geographical data. And I've been working for Norkart for almost a year now. And before then, I got my engineering degree from NTNU, the Norwegian University of Science and Technology in Trondheim. And I don't think any of my friends or family were especially surprised that I became an engineer, considering one of my favorite things to watch as a kid was MacGyver. The only guy who can make a nuclear reactor out of an orange and a paper clip. The fact that I became a coder wasn't as obvious. I didn't start to code until I started university, but I really liked it, and I decided to major in geoinformatics, because I found it really interesting to work with geographical data. And when I was writing my master's, I started looking into how neural nets and machine learning could be used together with geographical data, specifically how it could be used to automate the process of creating digital maps. So how are maps created? I'm not sure if you know this, but as you saw in the video, when they were mapping the rural parts of Tanzania, it was a manual process. They are manually detecting objects and drawing them. And the fact is that this is how maps are created. It's very much a manual process. So you have either satellite imagery or aerial images from planes, and then you manually, visually detect the objects and draw them. So it's a very time-demanding process. And to be able to help automate that would be very, very good. So the ongoing machine learning project that we have at Norkart is called AutoKart, which means automap. And what we've been focusing on so far is being able to detect buildings in aerial images. So you have an aerial image, and we want to automatically find all the buildings in this image by using visual recognition. But visual recognition is a very difficult task. Take, for example, the task of determining if an image is of a cat or not. Cats are often used as examples here. So this is a very typical image of what a cat looks like. And you can pretty easily come up with rules that you also can define mathematically for how you know that this is a cat. It has round eyes, a kind of triangle nose, 2 ears, standing on its legs, it has a tail, and so on. But this is also an image of a cat. And this, and all of these. So for a computer to be able to know if an image is of a cat or not, it needs to know what the common thing is for all cats. And even though we as humans are really good at this, we can see all these images and automatically know that they are cats, but we're not that good at knowing why we know it. We don't know how to define it. And with buildings, it's also the same. They come in different sizes, different shapes, different colors. Sometimes they're covered by trees or shadow. So to find a definition for how a rooftop looks like, or a building, that's also really hard. So that's why we need all the new cool technology, right? Machine learning, artificial intelligence, deep learning, and specifically the convolutional neural networks. So who here are familiar with these networks? Can I see a raise of hands? Okay, good. For those of you who are not familiar with them, I will now try to explain how and also why they work. And we need to start with the simplest part. What is an image? So this is what we see when we see an image. But the computer sees just a matrix with pixel values. And since this is a grayscale image, it's one matrix. If it was a colored image, it would be 3, red, green, blue, so RGB image. And what the convolutional neural networks does is that they use a process called convolution. So you have an input image. This is just a very simple example of what an input image could be. And then you have something called filters. And the filters are there to recognize specific features in an image. And which feature that filter can recognize depends on what values you have in the filter. And a typical feature could be a specific color, a straight line, a curve, a diagonal, and so on. So it's very simple features. But what you do is that you take this filter and you slide it across the input image, producing dot products. So you multiply the pixel value with the filter value, and you save the results into what is called an activation map. And what the activation value tells you is to what degree does that part of the image contain the specific feature that that filter can recognize. So if the filter can recognize the color yellow, and you get a high value in the activation map, it means that that part of the image is red. So you continue on, you slide the filter across the image. And you learn to what degree the feature exists in every part. But you do this not just with one filter, you do this with several filters, all producing different activation maps and different representation of that image. So you learn where in the image does it contain the color red, the color yellow, edges, curves, and so on. And then you continue on. You take new filters and you process them over the activation maps, allowing you to not only recognize these simple features, but also combinations of them. So combination of the color red and a curve, combination of the color red, a curve, and yellow, and so on. So the further into the network you get, the more complex features you're able to recognize. So with a car, for example, it starts out with these simple edges and colors, and it becomes more and more specific to a car. You can see that it's kind of wheels and the lower part of a window and so on, and then finally you can see that it's actually cars. Another important part of these convolutional neural networks is the pooling layer. And the pooling layers are used to downsample the size of an image. And you do this to get a reduction of dimensions, to reduce the amount of parameters that you have to calculate, because there's so much to calculate, so you kind of need to reduce it somehow. But you also do it to get a rotation and positional invariance, which means that you're generalizing what the image contains. You're kind of taking away some information and just saving the most important part. And so it won't matter that much if the image has some difference in color, if it's rotated a little bit, or if it's cropped. And pooling layer is often done with a max pooling operation, where you just save the highest value in subparts of the image. So that's how you downsample it. But you also need to be able to upscale the image again, because we don't want to lose resolution. And upscaling is done by a process called transposed convolution, where you have filters that learn how to upscale the images again. And it's not that important to know exactly how this is done, but you should know that there is a technique to upscale the images again. So the architecture usually looks something like this, where you have all the layers stacked after each other, the convolution layers where the filters are, and then the pooling layers to downsample, and then the upsampling layers again. But we need to train these networks. And what exactly does it mean to train a network? Basically, what you do is that you give the network a lot of examples of what you want it to learn with known output. So you make the network figure out how to map given input with given output. So if you want a network to learn to classify cats, you need to give it a lot of examples of images of cats. And not just these images, but a lot more. And you also need to give it images that is not cats, but similar to cats, like dogs and so on. And what the network does is that it tries to figure out what values can you put in the filters to find filters that recognizes features that are in all images of cats. So it just tests different values in the different filters to see what values it can put to find the features that exist. So it's all just like testing. And once it finds features or filters that can recognize correct features, it improves in accuracy. So it becomes better and better the more it's testing. But it's very important that you make sure that your model is generalizing instead of memorizing your data. And what I mean by that is that you need to make sure that your model is not just remembering and learning the exact examples that you're giving it, but that it's actually giving you a generalized model. So usually when you start training, you have this case of underfitting. Your model hasn't really fitted to your data yet. And if you keep on training and you're training correctly, you will find the generalization that you're looking for that fits your data pretty well. But then if you keep on training, you will have what is called overfitting, which is where the network or the model starts memorizing your data. So it starts fitting to the specific examples that you're giving it so well that it loses its generalization and becomes useless. And the way you avoid this is by splitting your dataset into different sets. So you have the training dataset, which is what the model uses for finding the filters. But in between training, you have a validation dataset. So you test your model to see how it's performing on a different part of your dataset. So what you're looking for is the point where your model is getting better and better at classifying samples in your training dataset. And it's also getting better and better at the validation dataset. But at some point, the validation accuracy is going to start decreasing, but the training accuracy is going to keep increasing. And this is the point where it starts to memorize the data instead of generalizing. So it's very important to make sure to be aware of this specific point. And then last, you have the test data set that you can use to actually check the performance of your data or of your model. Another thing is to make sure that your data set is actually giving you a realistic sense of the real world. So if you're training on, for example, these images of cats, that should be a good idea, right? They have different color, they're different types of cats in different positions. So that should be like a good idea to train on those. And if the model knows to recognize the top ones, it should be able to recognize the lower ones as well, right? Does anyone disagree? Because you should. Because what is common about the top 3 images, which has nothing to do with cats? Yeah. They all have grass in the background. They're all green. So what the model is learning is that for an image to be a cat, it has to have grass. So this is something to be aware of. So far, I've been talking about knowing if an image is of a cat or not, or if an image is of a building or not. But that's not enough for us. We don't want to just know if there is a building in an image. We want to know where in the image the buildings are. So we need to do what is called segmentation or a per pixel classification. So you need to split the images into 2 parts, one class for building and one class for background or not building. And the way you do segmentation is that you take small patches of the image. And you run that patch through a CNN, which stands for convolutional neural network. And then you classify that small patch, and you give that class to the center pixel. And then you continue doing this for every pixel in the image, giving you a per pixel classification. So you extract a small patch, send it through a CNN, and gives the class to the center pixel. So when you have a fully trained network, you can send in an input image, and it will give you a segmented output image. And this is how the network that we have used looks like. And this is based on a network called SegNet. And we also did some adjustment to make it work a bit better. but it's basically the SegNet architecture. And it was implemented using TensorFlow, which is a really cool open source machine learning framework from Google, which a lot of you probably know about. And I won't go into more details on exactly how this was implemented, because that's like a whole other talk. But if anyone is interested in looking at the code, I will show you a link at the end of the presentation to the repository, because it's all open source. But let's talk about the data set. When you're working with geographical images and geographical data, you're actually in a really nice position, because in Norway, we already know what all the aerial images are depicting, because we have digital maps. Someone has already done the manual annotation and recognizing all the objects and making data sets of them. So what I could do was to take existing vector data of buildings and aerial images of Norway with 1 point meter resolution, which is all data that we have at Norkart. And I could automatically map them together to create an image and building label. And it's all in the format called GeoTIFF, which is a way of having coordinates related to your images. So it's the so-called georeferenced image. So you know exactly where in the world the image is. So when you're able to recognize a building in the image, you know where the building is in real life as well. So this is an example of how the data set looks like. And this was all automatically created, which is super nice, because I didn't have to spend a lot of time creating the data set. I also wanted to test if having infrared images would give better results. Because when you have infrared images, you have data that is outside of the visible spectrum. So it was interesting to see if that contained information that would be better for the model to detect the buildings. And the results actually show that the infrared images are a bit better. So the images that you will see now is from the infrared image dataset. And the results looks like this. So the green yellowish areas are the pixels that are classified as buildings by the network. And you can see that it fits to the buildings pretty well. Almost all the buildings have most of their pixels classified correctly as buildings. But there is one pretty obvious problem here, and that's the shape of the buildings. It's all very blobby. So if you would remove the aerial image underneath, you wouldn't necessarily understand that it's buildings. It's all like blobs. These are two more examples where the shapes are a bit better, especially on one of them, but it still has problems with the corners especially. But I do like this example really well. If everyone can look at this image and try to see if you can recognize the buildings. When I first saw this image, you kind of immediately look at the lower part of the image, right? That's the interesting part when you're looking for buildings, because the rest it's all trees, right? Maybe. So the lower parts, that's kind of obvious. But let's look at what the network says. It does recognize the buildings in the lower part, but it also finds two buildings in between the trees. And if we look at the ground truth, it's correct. There are buildings in between the trees, actually two more that the network didn't find. But it still shows how these networks are very precise. They will always look at every single patch of the image. While we humans, we get tired after looking at images for hours and detecting buildings. Like, I could pretty easily imagine that I would not find the buildings in between the trees after a couple of hours of doing this. So what can this be used for? One thing is that it would work well for doing calculating the percentage of an area that is covered by buildings, because you don't need the correct shape for that, right? And this could be used for change detection, figuring how fast is a city growing, looking at images from 10 years ago and now. You wouldn't need the building data, you could just have the images and that's it. And it could also be used to detect unregistered buildings. And I wanted to test how that could work. So I did a kind of proof of concept project, thank you. And saw if I could use this to detect illegal buildings. People building houses and not telling the municipalities and thinking like no one will ever figure it out. So I took a whole new area and I ran it through the model and detected all the buildings. And then I compared the results to our existing data to see if I could find areas that didn't correspond. Areas where a lot of adjacent pixels were classified as building by the network, but I couldn't find a building in the dataset. And I did actually find a lot of buildings, and I could look through a huge area and then just only look at the candidates of new buildings. And of course, there were a lot of false positives, like pixels classified as buildings that weren't actually buildings. But I could pretty fast go through and find a lot of like small houses in people's backyards and stuff like that. And this is one example of a building that I found. And this building should definitely be in the dataset. This is not like a small house that no one needs to know about. And finding these sorts of buildings, that could be very useful. And you could do it fast and not have to sit and look at all of this manually. And this starts to feel like something like MacGyver could do, right? I can find illegal buildings with only images and an algorithm. But let's go back to where we started. Can we use this in order to map the rural parts of Tanzania? And that should be possible. I mean, we have a model that can detect buildings. But there are a few issues. One of them is that Tanzania and Norway doesn't exactly look similar in aerial images. So you can't really expect a model that is able to recognize buildings in Norway to detect buildings in Tanzania. So we would need a new data set specifically for Tanzania. And luckily, Crowd2Map has already done a lot of mapping in Tanzania, so we could use that to create a new data set and then fine-tune the model, meaning that you train it a bit further so that it can learn the new images. But we still have the problem of the accuracy, right? The blobs and the edges. And the network that we have implemented, I implemented that network a year ago. And a year, that's a long time in the machine learning world, luckily. So a lot have happened since then. So today, there are a lot of segmentation networks that work way better than SegNet do. So you have UNet, which works better, SegCaps, which works better, which is based on capsule network, which is really cool. So you should check that out if you're interested, but that's like a whole other talk. You have MaskRCNN, FCDenseNet, DeepLab v3+, and all of these would work better than the network that we have. So I started looking at the DeepLab v3+ network, which was open sourced some weeks ago. And if we're able to use that, we would get way better results. Unfortunately, I'm having some issues making it run with the binary data set, so if anyone has done that or knows how to do it, please come and talk to me afterwards. But when I figure this out, we will have better results. So that's going to help. But assuming that it will solve all the problems, I don't think that's likely. I think that based on the results that I've seen that people have gotten from this network, I think we're still going to have problems, especially with the edges of the buildings. We're not going to have like the nice straight lines. So we recently started a project called MapAid, where we actually have 3 summer interns that are helping us make a kind of post-processing tool for the machine learning results. So the idea is that this tool will, first of all, try to make the results more usable. So the tool should, first of all, vectorize the data. So instead of having just images, it should be like geographical information. Get it into a GeoJSON format. And then, of course, visualize the results, because even though you can look at how big of a how much of the pixels are correctly and falsely classified, you need to visualize the results and see how it actually looks. And then the idea is to create an algorithm that can actually straighten out the edges, because we know that the buildings are straight, so this should be possible to do. And also, we want to find the areas where the model is performing badly. And in that way, we could improve our data sets. So this is an example of a building that there might not be that many of. So the data or the model hasn't seen that many examples of it. So detecting these areas and then creating more instances of this into the data set would make the model better. So, and this could be done either programmatically or having the user detect these areas. So by using this, we would get better data sets, both for areas like Tanzania and Norway. And then we could send those data sets into whatever model is the best at the time. Now we're probably going to change our network from SegNet to the DeepLab v3. And then we could use the MapAid tool to both find the areas where the model is struggling and send that back to the data sets, but also improve the results further. So this is how we think that it's best for us to work, because we're not like a bunch of researchers that can find the best algorithm for how to do this. Google and Microsoft and everyone else is doing that. So as I mentioned, the SegNet network is open source. So if anyone's interested, you can go into my GitHub and look at that. And that was it. Thank you so much. Are there any questions?
Have you tried using infrared pictures taken in the winter? Tried the network of that?
No. Do they take infrared images in the winter? I'm not sure. I don't think we have them.
Buildings would probably show up better there.
Yeah, could be. Yeah, that's a good idea. Anyone else? You can just come and talk to me afterwards. And I should also mention that Norkart is hiring both back-end developers, front-end developers, and if you're interested in machine learning, I would love to have more colleagues working on that. So, did you have a question?
Yeah. Do you recognize houses with grass roofs?
I don't actually know. I'm hoping to figure it out with the MapAid tool, because I'm guessing that is something that we're having struggles with. And if we can detect that, then we're going to send a lot of those images back into the data set. OK, thank you. Oh.